So I'm holding a spec sheet here, and the name on this thing is, well, it's practically a password. It's the NTI E-STHSB-N4085IND-35.
Oh, that one. A name only a motherboard could love.
Seriously.
Yeah.
But if you can look past the alphabet soup for a minute, this is not your typical hallway thermostat.
Not at all. This is a high-performance industrial sensor, and it's built for places that would eat normal electronics for breakfast.
And that's really the mission for this deep dive, right? We're using the specs from HDTV Supply and NTI to figure out how this kind of hardware survives.
Exactly. How do you get precise monitoring in freezing cold or blistering heat? And why does a feature like, say, digital signaling become the difference between a safe facility and a total disaster?
Well, the survival part is the first thing that just jumps out. I mean, this unit operates from minus 40 degrees Fahrenheit all the way up to 185.
That's minus 40 to 85 Celsius. And that bottom end, that minus 40, is so significant. That's where standard components just, stop acting like circuits and start acting like bricks.
It also does humidity from 0 to 100%, so long as it's non-condensing, of course.
So you're spotting moisture that could rust out equipment long before you'd ever see the damage.
What's really fascinating, though, is the precision you get inside that chaotic range. Usually when you build something to be rugged, you have to sacrifice accuracy.
Right, there's a trade-off.
But not really here. It maintains plus or minus 0.7 degrees Fahrenheit accuracy in the normal range.
And even in that extreme cold, down near minus 40, it only drifts to about plus or minus 1.6 degrees. For an industrial freezer or, I don't know, a remote weather station, that's incredibly tight.
Okay, the accuracy is impressive, but I think the real lifesaver here is how it actually talks to the system.
The RS-485 communication.
The digital output, yeah. This is huge, because if you've ever worked in a factory, you know analog sensors are a nightmare.
Oh, the signal drift is terrible. You think it's 70 degrees, but the magnetic field from a huge motor nearby makes the system report 90.
It's like a ghost in the machine.
It is. Think of it like shouting across a noisy factory floor versus sending a text message. The shout gets garbled, lost in the noise.
But the text message...
The text arrives exactly as you sent it. That's the RS-485 difference. It just cuts through all that electrical noise, so the number you see on the screen is actually reality.
And you don't have to be standing right there to get that message. This specific unit comes with a 35-foot cable, which is fine, but you can custom order them up to 1,000 feet.
But there's an even bigger unlock here.
The fiber converter.
I saw that.
Right. You pair this sensor with the EFSC fiber converter, and the range just jumps exponentially.
It goes from a few hundred feet to 1.2 miles. That's 2 kilometers.
I mean, you could have the sensor inside some remote storage bunker, and the main unit could be in a secure office a mile away.
You just have to make sure you check that main unit before you run all that cable. It connects to the EnviroMioGEX series, but there's a little trap here with the E2D unit.
The Rev C issue.
Yeah, that's a classic. Gotcha. It really is. It catches people off guard. If you've got an older E2D unit, this sensor just won't talk to it. You have to physically check for Rev C on the unit.
How can you tell?
Look for 2 power inputs. If it doesn't have 2, you've just bought a very, very durable paperweight.
And that industrial-grade durability, that probably explains the price tag, too. It's listed at $242, which feels a little steep next to a home sensor.
Well, you're not really paying for a thermometer, are you? You're paying for insurance.
That's a good way to put it.
In a data center or a lab where a server meltdown or a frozen pipe costs thousands, maybe millions, $242 to know exactly what's happening through all the noise is a bargain.
So it's really a safety net for critical infrastructure. It's rugged enough for the Arctic, it's smart enough to ignore interference, and it can see for over a mile.
It makes you wonder, though, about the future of design. If distance and environment are no longer barriers to getting precise data, how does that change how we build things? Do we even need human-accessible control rooms near dangerous machinery anymore? Or can we just, fully decouple the monitoring from the risk itself?
That is something to chew on. Thanks for diving deep with us.